Thank you so much for being here. Thank you for having me. It's a pleasure. You know, as your dean mentioned, I have a long career as an administrator, chairman, dean, chancellor, president. But whenever I'm on an airplane and the guy next to me says, "So what do you do?" My answer is always, "I'm a mathematician," because that's what I feel more at home. So this is more my home than the office where I run Chapman University. So I appreciate the opportunity to speak with you a little bit about what I do, some of the work I've been doing. In super oscillations, I've been working on this topic maybe for the last 8 years or so. And what I'd like to do today is to give a very general introduction. So I always try to give talks that even non-specialists can participate. I remember my advisor when I was in Maryland used to tell me, go to every talk, because there is always something to learn, but make sure you bring something to do. Don't sit in the first row, sit in the back, so when after 10 minutes you don't understand anything else that has been said, you can work, you can grade your papers, think about your stuff. So, and he was right, yeah, as always, my advisor was right, and so I always try to talk about stuff that hopefully can be understood at a larger level, and then, you know, I'm happy to later on to talk in more details if there is any special interest. So what I like to do is to first of all describe what super oscillations are, the basic ideas. Then I'm going to look at the first important problems that we looked at when we were given this topic to analyze, and that was how do super oscillations evolve when we take them as an initial value for a Schrödinger equation. As it turns out, the problem actually then, at least the way we dealt with it, requires the use to abandon the real line and move into the complex plane and the use of something that are called the infinite-order differential operators. This is not a topic of very large use, but I think this plays an important role in this discussion. Now, super oscillation ends up being a very special case of a much more general phenomenon that I won't really have the time to get in today, but I will at least mention is the notion of supershift. So I'll show you what we mean by supershift. I'll show you also why it's relevant to this discussion. There is at least one very simple example in which supershift becomes important. I give 2 or 3 ideas about some of the current research about these, and then I close with a few references, and for anybody that might be interested in looking a little bit more in detail at these things. Okay, so let me start with the basics. So the definition, the rough definition of super oscillation functions, oscillating functions, is that band-limited functions which oscillate faster than the highest frequency that they contain, which seems like almost a paradoxical definition, right? Because if you're band-limited, that's how much you can oscillate. But we will see why this kind of large-scale definition actually reflects in the actual definition and why that is possible. And where do they originate? Well, they really originate in 2 different areas of physics. One is the theory of weak measurements due to Yakir Aharonov. Many of you know his name, if nothing else, for the Aharonov bomb effect, one of the most important phenomena of quantum physics. And he is the proponent of this theory that is called weak measurement that allow calculation of values of observable that go way beyond the numbers that one would expect with the traditional measurement. So he wrote this paper in 1988 that with the paradoxical title of how the result of a measurement of a spin 1/2 particle can be up to 100. That obviously because you're measuring what he calls the weak measurement. And as you measure weak measurement, some interesting mathematical phenomenon appears, and that's a phenomenon that goes under the name of super oscillation. In a completely different direction, Sir Michael Berry from Bristol studied super oscillation from a different perspective, namely from a perspective of optics. And in fact, most of the work, most of the applied work that is done now on super oscillation comes from the field of optics, and the purpose being to use them to do super resolution. Okay, so these are kind of the origins of this, but let me tell you what we consider the prototypical function. I call it prototypical because if you read any paper, and there are hundreds of papers on super oscillation, they all start with this function. So This function is going to be in page 1 on every paper one read. Very simple function. X is a real variable, n is an integer, and a is a parameter bigger than 1. And the function is the cosine of x over n plus ia sine of x over n, all of this power n. So a very simple, innocuous looking function. Now this function can be transformed by using Euler's formulas. So instead of the cosine of x over n, you get e to the I x over n plus e to the minus I x over n divided by 2. And instead of ia sine, the I cancels with the denominator, so now you get a times e to the I x over n minus a e to the minus I x over n. So then you collect, you factor them out, and then you take the nth power, so use the Newton binomial formula, and what you get is this expression here. So now we have rewritten, that's exactly the same function we had before. And these coefficients C, J, and A are the coefficients that come out of the binomial formula. So you have this, you see that kind of unpleasant coefficient because first of all they oscillate, they are one positive, one negative, because of the minus 1 to the J. And they also grow like A to the N, so they grow very, very fast as A becomes larger. So these are coefficients, you put them there, and then you add up those exponentials, and you get the original function. So far what we've done is nothing but rewrite the original function in terms of its Fourier expansion, if you want. Okay, so now we notice two things here that are important. The first one is that when you take that function, you take the limit for n goes to infinity, this function converges uniformly on every compact set to e to the IAX. Why is that? Let me go back a couple of slides, just a second. The cosine of x over n is up to a second order, the order is 1, and the sine of x over n is x over n. So you get 1 plus IA x over n to the n, and that gives you the exponential. On the other hand, as we saw in the previous write-up of the function is a finite sum of exponentials whose frequencies, the coefficient in front of the x, are this number kj, 1 minus 2j over n, which are all bounded by 1. And that's why they're called super oscillations. So now I'm going to go back to the previous slides again. So you have this finite sum. The exponents have frequencies that are all bounded between minus 1 and 1, right? Because j goes from 0 to n. So when j is 0, you have 1, and when j is n, you get minus 1. And yet, this function converges to e to the IAX for a arbitrarily large. And so the term that was used is super oscillation because they oscillate apparently only very little, but then in reality you get this large. Now, first of all, why is this possible? Well, it's possible because when you let n go to infinity, this is not really a series. And it's not a series because the coefficient depends on n itself. See, if you add summation from j to 0 to n of cj e to that exponent kjx, you will have, and then you take the series, you would have an infinite series of exponentials whose frequency are between minus 1 and 1, and that would never, there is no way you can generate e to the IAX. What makes this, the peculiarity here is that every time you increase n, you also change the coefficient. So it looks like a series, but it's not a series. And that's the reason why the phenomenon, the apparently strange phenomenon, is not strange at all, because you have to kind of play a trick there. Okay, so there is an interesting alternative approach. I'm not going to talk about this today, but it's important to kind of in the background. There is another way, for example, that one could build a super oscillating function. First of all, the example I just gave you required the coefficient to be this 1 minus 2j over n. What are these 1 minus 2j over n? Think about it, as n grows, these are a bunch of numbers near the origin, but they're very specifically chosen. Well, it turns out that it doesn't matter. You can choose any number, any sequence in the kjn between minus 1 and n, and then you can generate exactly the same phenomenon with this particular expression. The proof is also not very complicated, it's just the use of van der Monde determinant. This function fn has all the derivative of e to the IAX up to order n, And so what you see here is that this phenomenon is really an interpolation phenomenon, because what you have here is something that is really the Lagrange interpolation formula. So this plays a huge role in some of the more recent work on superoscillation, but essentially tells us that the phenomenon of superoscillation is really a kind of an interpolation problem, and then also kind of an extrapolation problem, because you know the function only in an interval between -1 and 1, and yet you can determine outside those values. Okay, so this I thought it would be important, because in many other papers that you may read that are quoted the reference that provide later, this is the function that is used to demonstrate the phenomenon. So there are millions of questions, of course, like always, that one can ask about stuff. But the question that Aronov and his colleagues ask is the following, and Michael Berry as well, he worked on this for a while. Suppose you have a superoscillating function. And I should clarify that I always say superoscillating function, and it's a little abuse of wording, because in reality it's a sequence that superoscillates. But let's suppose we have, and we take as initial value of the Cauchy problem for the Schrödinger equation. Yes. The physical question is, when you do this, does the superoscillating phenomenon continue? And the reason why this was important is because, as I mentioned before, superoscillation are being used to solve problem of super resolution. So the question is what you do, you beat the resolution limit, you take waves that are, frequencies are between -1 and 1, and then you combine them in this way to generate this superoscillating effect that will allow you to separate very close objects, improves your resolution. The question is, how long will the phenomenon last when you evolve it? So that was the basic question, and I'd like to discuss a little bit how we address this question, what are the main mathematical instruments, because there is a lot of interesting mathematics, I think, that comes out of here. I'm going to deal with the simplest possible case, which is when v is equal to 0. But the reason why I choose v equals 0 is because then I can actually do it in 2 slides. But we have actually results in the literature for a much larger, more complex set of potentials. So the idea, the technique, and the strategy that I'm going to illustrate in the next 2 or 3 slides is completely general. When v is not 0, the calculations are much more horrible, and I couldn't really describe them here, even though I'm going to give one example, at least for a quantum oscillator. So what is the strategy? Well, first of all, we look at the Cauchy problem. That's our starting point, where Fn is a superoscillating sequence, H is the Hamiltonian, and as I said, there are a very large number of cases that can be addressed with this. One of the open questions, though there is a group of people now working at Tulane University and another Washington University in St. Louis, they are having some interesting idea to answer the problem, which is, can you tell me for which Hamiltonian H we can apply the technique that I'm going to show you? So we have a large class of solutions, but the question is there any characteristic that you can show me about the Hamiltonian that will allow me a priori to say whether or not I preserve superoscillations? Next step is to find the solution. This is where things get more complicated when you have complex potentials. Usually you need the green function, and then you have to do some work to write out the solution. And then you try to calculate the limit as n goes to infinity of those solutions. And then, if in fact this limit is superoscillating, then what you have, well, first of all, you answer your question, yes, the superoscillation remains, but also you discover a new superoscillating function by just setting, for example, x equals 0. We see an example in a moment, and then you have another superoscillating sequence, or even you can have superoscillating sequence in multiple variables. So that's a general approach. Now, what is the real difficulty in the approach? As I'll show in a moment, is this second bullet, which is to compute the limit of those solutions. And the reason is, as I'll show you, is because the solution can be written in a very complicated way that will require some fine topological analysis to determine whether or not we can calculate the limit.
Already know that as a probability amplitude.
Sorry, say again, we know?
At this stage, we know that the psi has the quantum mechanical.
Oh, yes, we know. Yeah, well, it really depends on the particular system, but you actually have your function in front of you, so you know exactly what that represents. So let me deal with the case of V equals 0. And again, for simplicity, but a lot in the literature shows you how to deal with more complex situations. So the first observation is that you can write in a very simple way the solution. That's usually not always the case. In this case, you write it very simply. It's a sum. So we start with our Fn, our original function, which is the super-oscillating sequence. And the solution to the Cauchy problem is this new sequence in which you have two exponentials that appears. Now you can see this by inspection, because if you take the derivative with respect to t, what do you get? You get minus I k squared, is a coefficient. And if you take the derivative with respect to x, you get I k once. And then you take it a second time, so you get minus k squared. And because of being in front of here, then it's clearly satisfies your Schrodinger equation. So there is nothing special here. So, but now what I'm going to do, I'm going to rewrite this component, the t component, as an infinite series. And this will allow me to show that my solution, I'll show this in the next slide, but my solution can actually be rewritten in this way. And this is kind of the general result that we have here for V equals 0, but then we are able to show in a very large class of examples. So what this is telling us is that the solution of the Cauchy problem to the Schrodinger equation can be written as some infinite series, not always the same, obviously, some infinite series of derivatives of the function Fn. So there is a map from the family of potentials into the family of this infinite series of differential operators or derivatives. So this is what you would call, that's a name that appears in a couple of slides, infinite order differential operators. This is a very general thing that works in a large set of situations, even though in many cases these differential operators here are very complicated. So here we have a very simple case, but nevertheless, the fact that you can write your solution as an action of an infinite order differential operator on the original function is the key factor in the solution. So let me show you why this is the case. As I said, I'm going to show it by replacing the second exponential there with an infinite series. So e to the minus it k squared is an infinite sum of minus it k squared power m over n factorial. As I read it, I'll never mention the j, it's too complicated. So I rewrite it. This minus it power m over n factorial that I can take out. And then I have kj to the 2m, and then e to the I kjn. But now I know that this kj to the 2m is nothing but the second, the 2m derivative of e to the I k xj up to a sign that cancels with this sign, so I get an empty here. And so now I have that my function can be written as the action of this infinite order differential operator on the original function. So the reason why this is helpful is because it will give me an instrument, or at least a chance, to calculate its limit, which otherwise may be very complicated to calculate. So this is the operator u that appears in this elementary proof I just gave. So the question is to show that this u acts continuously on the function that we are working with. So what I like to calculate is the limit of the psi n. But the psi n are nothing but the operator u applied to Fn. And so if I can interchange the limit and the operator, I get u of the limit of the Fn, but the limit of the Fn is the exponential, e to the iax, because that's how we started. And when I apply u to that exponential, I get e to the iax minus ia squared. So if I can do this, then obviously what I've shown is that I start with a super oscillating function, Fn converging to e to the I ax. I solve the Cauchy problem. I have a new function that is now a function of two variables, x and t. And when I take its limit, I get exactly now a super oscillating function in two variables, e to the I ax, which is the same thing I started with, and then e to the minus ai a squared t. So this would apparently give us the solution of the problem, tell us that it's possible. And the question, though, is, can I do this switch? And even more important question, what is that operator? So here is where it's where the theory of topological vector spaces will come into the picture. I have to confess that when we wrote the first article on this, and I think we sent it to the Proceeding of the Royal Society, and the referee accepted the paper, so the paper was published, but made some snarky comment to the extent that, well, you know, why are these people, which is us, the writer, making such a big fuss about the interchanging between the limit and the operator? Now, we're mathematicians, or at least for mathematicians, this is always a very delicate thing. You can't interchange the signs between an operator and the limit unless you know something about continuity. So that's why the major part of our paper was about that particular aspect of the calculation, and I'm going to tell a little bit about it. But that is really the core. Now, the first question, though, the one has is that these operators are not even well defined for real functions. The infinite sums of derivatives, it's not a good operator. Part of the reason is because infinite sums of deltas is not a distribution. So it's you can't really even think about using that operator on real functions. Now here we are lucky because the function we are working on, and that becomes important in a later stage, the function we are working on are finite sum of exponentials. But these exponentials are really the restriction to the real line of holomorphic functions in the complex plane. In fact, and this turns out to be very important, they're restriction of functions which are entire. In other words, holomorphic everywhere. One has to remember that if I have a real analytic function on a real line, this is the restriction of a function which is holomorphic somewhere around. But that somewhere around doesn't have to be everywhere. For example, 1 over 1 plus x squared is perfectly real analytic and extend to a holomorphic function is 1 over 1 plus z squared, but this is not entire because plus or minus I are singularities. Much of the argument that we discuss here depend on the entire nature. So let me take a quick detour to infinite order differential operators. So first of all, the classical definition of an infinite order differential operator, notice that here I move to the variable z, so now we are in the complex plane, is an infinite sum of derivatives, but with this special condition on the coefficients. So this means that that particular condition means that this function, which we call the symbol, has some very special growth conditions. It's what mathematicians call infra-exponential type, or exponential type 0. And I'll describe in a second what it means. So the theory, if you look at the theory of infinite order differential operators, you will always find that this is a central condition in order for this to actually be an operator that acts as a sheaf of homomorphism on the sheaf of germs of holomorphic functions. As we will see in our case, that's not what happens. So that makes things slightly more complicated. A good example of an infinite order differential operator is something whose symbol is the hyperbolic cosine of the square root of the derivative. Well, shouldn't worry. I mean, this is a kind of a funny way of writing it because the square root of a complex number is a complex object, but the reality is that because the hyperbolic cosine is only even powers, that's what this really means. And so this is the expression of this particular differential operator. It was one of the first that the Japanese school studied when they entered into the analysis of this object. So this is a particular example. This function has the right growth, so it's an infra-exponential type. While in general, not every infinite sum of derivatives is a differential operator. Simplest example, something the physicists know obviously very well. When you take the exponential corresponds to the translation. So what we have is that even though this looks like an infinite order differential operator, in reality it is what we call a convolution operator. It's not an operator that acts on the germs or on the sheaf of germs because it moves the support. So I took a couple of moments on this aspect because sometimes we use the word infinite order differential operator as an abuse of terminology, just to refer to infinite series of derivatives. But we have to remember that in many cases these derivatives don't act on the space, a sheaf homomorphism on germ holomorphic function, and this makes everything else a little bit more complicated. So the question is going to be to see, when I get these operators, let me go back just a couple of slides. So here, the operator that we are looking at is this infinite sum of 2m derivatives divided by m factorial. The coefficient in front is not going to bother us. What I will want to do is to replace that x with a z and see what kind of operator do I get. And it turns out that that's not an infinite order differential operator. It's actually a convolution operator. In other words, it does not satisfy this stricter condition. So let me take a comment on this. So when you have an infinite order differential operator in the strict sense, this is can be thought of as the Fourier Borel transform of analytic functions carried by the origin. And so it will map holomorphic function to holomorphic functions. The operators that we are looking at, on the other hand, will add some growth conditions because they don't grow in the way that we'd like them to be. The symbols, the function P of I zeta, does not grow with the condition that would be necessary for it to become an analytic function. In fact, I mentioned before the infra-exponential type. That's a space of functions that will represent the infinite order differential operator. So we need to look at a couple of additional spaces here that allow us to work with these operators that are actually convolutors. So let's say two positive real number P and Q, and let's say that 1 over P plus 1 over Q is 1. Then we have two important spaces. The first, APC, is the space of entire functions such that there are constant A and B that bound the growth of f. So mod of f of z is bounded by a e to the b mod z power b. So these are functions of exponential type p. Then there is the corresponding, which is a q0, which is a function of infra-exponential type q, which are such that for every epsilon, there is an a sub epsilon for which f is limited in that way. So these are two different spaces, and it turns out that they're dual to each other. And that's a very important result. In other words, if I have a function here, this function here will be the symbol of a convolution operator that acts continuously on this space. And the function here is the symbol of a convolution operator that acts continuously on this space. So this allows me to study the continuity among these spaces. Now, this is not as trivial as my statement may appear, because the topology in this space are kind of complicated. There is an inductive limit topology in one, there is a projective limit topology on the other, and the calculation of the actual fundamental set that allow you to study continuity is not absolutely immediate. But let's just say that they're now well understood, and so we understand these spaces, we understand their topology, we understand what continuity means on them. Example, the function xc, which is the entire function of exponential growth, is a1. So when I put 1 here, so I have b mod z, I have function of exponential growth. They're important because they represent the dual of the space of analytic functions. So if you have h of c, entire function, and now you look at an analytic function that's a continuous linear map from h of c into c. This object you can take Fourier Borel transform, and through the Paley-Wiener theorem, it turns out to be isomorphic, topologically isomorphic. type to the space X. If you take those more refined operators, so not just every function of exponential type, but function actually of infra-exponential type, so take again q equal 1, so I have a sub epsilon e to the epsilon mod z, then you get the space which is isomorphic to the Fourier-Borel transform of analytic functions supporting the origin. Now that's a very interesting space because for those who are familiar with hyperfunction theory, those are actually hyperfunctions supporting the origin. So there is a very interesting theory that plays some role, but not in what I'm saying today. Okay. So I think I said the general result already, that the space AQ0 is a space of symbols or linear continuous infinitary differential operator. I should have said convolution operators on AP and vice versa. We have a very good description. We know exactly, we know kind of everything instead of not only what this operator look like, but also the coefficient, the conditions on the coefficients of the series, the Taylor series. So the question is, okay, let's go back to the space that we started before, this operator we started with. On which space of entire function does this operator act continuously? Well, it turns out that this space is A to 0, and this space, because the symbol of this is really e to the z square, or iz square. So it's a function in A2. And so the space with the axon is A to 0, and the space contains exactly the finite, the sequences of finite sums of exponentials. So this allows me to do the trick that, okay, wait a sec. It allows me to do the trick of interchanging the limit and the so let me, before I get to the next slide, let me summarize how we solve this problem. So you start with the Cauchy problem, and initial value is a super-oscillating sequence. You take this, you look at the solution. In our particular case, that was very simple, but imagine even a more complex case. Then you work on the solution, and that's where much of the technical challenge is, to show that that solution can be written, in fact, as a convolution operator of some sort, acting on the original function. So there is a direct representation from the V, the potential, to the differential operator or convolution operator that acts. Now you have a problem in trying to exchange the limit sign. So what you do is you move your problem, you replace the x's by z. So now you complexify your problem. Now you go in the complex plane. The complex plane, you have this infinitary operator, you know how they operate, you look at the growth of the space, you find where do they fit, and then you show that in fact you can interchange, you have continuity, and then you can restrict back to the real axis, and so you get your solution. So it's a very, well, I would want to say convoluted process, but that would be fun. So you solve the problem, then you move to a complex state, you show that you can do the limit exchange, and then you go down and you get the result. So, as I said, this is something that works in much more general cases. What I hope is clear that there is a lot of hidden stuff here, so I don't expect people to say, okay, that's obvious what happens. There is a lot of fancy hidden stuff, in particular the topological aspect. But now let me give you, I want to talk about a little, just one slide, I think, about generalization of the situation. When you look at the super oscillation that we discussed so far, just the simplest example that we looked at, what really happened there? Now, we look at e to the I ax as a function of x, but now I'm asking you to look at that as a function of lambda. So as a function of lambda, of the frequency, you have a family of functions. For every lambda, you have a function e to the I lambda x. What a super oscillation phenomenon tells you that it's enough for me to know a few, or many, but limited values of a lambda for this family to be able to calculate the family wherever I want. And that's what we call supershift. So for supershift, you have a family of functions, and then we say that we have supershift if there is a sequence of finite linear combinations indexed on a bounded set, doesn't have to be one, but a bounded set of lambda that converges to phi sub a, no matter how big a is. So when you look at the case of exponential, I'm just restated differently what I said before. But the notion of super oscillation took the name from the fact that this lambda is an oscillating factor, it's the frequency. But there are situations in which that's not what happens. First example we have is what do we do if we solve the same question I posed before, but now for the quantum oscillator. So the V is now equal to x squared. So that's the next easiest case. I showed you V equals 0, very simple, 2 slides. V equal x squared is a little more complicated, but it's not horribly complicated. And this is what you get as a solution. You get a much more complex function. It doesn't matter how you get there. Probably everybody in this room knows how to do it. But what happens here, and now you have this kj, these frequencies that appear in my Fn, are now here as coefficients of the tangent of t, and square, and here as coefficient of x over cosine of t. So they're not oscillating factors anymore. But what we show is that I can write the solution of if I solve the Schrödinger equation for V equal x squared, so the quantum oscillator, and I take as a Cauchy data e to the I ax, I'm going to get this function with a here and a here. This family of functions is my family of function f there. So now I have a family of function, and if I know the values of these functions, only for very small numbers of lambda, only lambda between -1 and 1, it's a discrete set of values there, I can reconstruct the function anywhere. And that is a result that is, in a way, the supershift phenomenon appears kind of odd, because it's telling you that for these families, if you know something near the origin, you know it everywhere. And that a priori seems like a very, very strong property. In fact, it is a strong property that is not true in a general setting. So this raises several questions, one of which I'm going to have just a couple of current research problems that I will talk about. But there is another way to think about this. Think about real analytic functions. What is the property of a real analytic function? The fundamental property is that if you know the value in the origin of the function and all of its derivatives, then you know the function everywhere. That's kind of a powerful property. So what you do is you have infinitely many pieces of information in the origin, and then you know the function everywhere. What this concept tells you, that now what you do, you still have infinitely many values at the origin, but they're not the value in the derivative. You know the value in infinitely many points near. Remember, these lambda j, kj that we use here were very specific, right? 1 minus 2j over n. But as I showed in the other example, they could be arbitrary. So I give you an arbitrary but infinite number of points between -1 and 1, or -1 half, 1 half, it doesn't matter. Using those, I can reconstruct the function everywhere. So in a way, one can think of this as some kind of analyticity property. Super oscillation property is really a property that, and in fact, the main example we started with is the exponential, which is clearly a real analytic function. In fact, it's even more, it's a complex analytic function. In fact, it's an entire function. And so the question is to ask whether there is a relationship that can be established there. Well, it turns out that this question is much more complicated than we originally thought when we started working on it. So we have a couple of papers on this, and we really don't have yet the final answer. So first of all, it's very simple to show that if a function is the restriction of an entire function, you always have this phenomenon. So analyticity, holomorphic analyticity, implies supershift. It's also not too difficult to show that there are examples that supershift. There is an example due to Kantorovich that he came up with for very different reasons that shows that supershift does not imply analyticity. But the real question then becomes, what is the extra step? So analyticity is going to be equal to supershift plus something. So we have a property that is clearly stronger than being infinity, but not strong enough to be analytical. And so the question is, where do we locate that? So this is very, I mean, we've been working a lot on this. It brings in stuff from interpolation theory, Bernstein approximation theory, and we're still waiting for this. The second interesting possibility is to look at super oscillations as weak values of momentum. I said before that the original arrival of super oscillation was when Aronov introduced this weak values for the momentum operator. It turns out the super oscillation arises there. But what if one takes other operators and other observables? Can I redo a theory of super oscillation for those operators, and what does that mean? And finally, this is really mostly application that our physics colleagues have been working on. How can you utilize these properties for imaging? There is quite a bit of work already done, as I said before, in super resolution. One of the challenges is the amount of power that is necessary. You remember that when I showed at the very beginning these coefficients that we have the Cj in front, they grow like a to the n. So what happens is that the amount of power that is necessary to create this phenomenon that will allow you to do resolution is very, very significant. So the question is, can we play some tricks so that that's more actually affordable? We have already experiments. I say we, but I shouldn't take I have done nothing with the experiment, but I've seen experiments in which actually this is used for really significant improvement of super oscillations on resolution, but the duration tends to be very limited, and the amount of power to be expended tends to make it not really practical. So there is a lot of work here in trying to see how this can be done. There are applications of these to radars, for example, and similar analysis for radar can improve the resolution of radar imaging by using, again, this trick. So when you think about the original trick, it's really quite simple. You just superimpose cleverly waves, simple waves in such a way that you create a very high frequency. So there is, you can trivialize it, but how that's done is super complicated. I want to give a few references and make a couple of comments on each one of them. So most of the mathematical aspects, at least until 2017, are in this memoir of the American Mathematical Society, in which we present the problem and we analyze several different cases of different potentials. We also study some interesting variations. For example, when you have a Dirichlet series, a Dirichlet series is an infinite sum of exponentials with arbitrary large frequencies. So what if you replace the arbitrary large frequency with smaller frequencies using the super oscillation trick? What if you now write everything in terms of, so can you write this Dirichlet series by only using limited frequencies for your factor there? There is, I think, a lot of interesting work to be done there. There is an interesting connection between the super oscillatory phenomenon and the very famous Weierstrass function. You remember it's a function we studied first year in college, right? It's nowhere differentiable, but continuous everywhere. The function is a clever sum of sines or cosine with frequencies that change. So it turns out that there is some connection there with some super oscillatory phenomenon as well. So there is a lot of really interesting mathematics here. There is a large amount of work to be done on the topologies of the space that allow you to do the switch of the continuity that I did before. If you're more interested in applications, maybe a real great introduction is this work, is a roadmap by the Journal of Optics. You're probably familiar with this. Journal of Optics publishes this roadmap. They choose one topic, and then they invite 30 people who are experts on that to write different short articles. So there is in here, there is a 4-page article by us on the mathematical aspect, but the reason that this might be interesting is, on the other hand, because there are lots of applications. There is a discussion about the issue of power that I discussed before. There is a discussion about how you can make effective the super resolution. There are discussions on how does this process compare with evanescent waves, and so on and so forth. So this is really about the math. This is more about the physics. And then some other articles that explore some of the topics that I briefly touched upon. The first one is all about the infinite order differential operators. So, or as I more appropriately here, we say continuous endomorphisms because they're really convolution operators on these spaces. This is something that, as I mentioned before, the Japanese school has been working for many years. It was one of, in connection to the theory of hyperfunctions. And so here is where you will get the entire description of what happened with these operators. I mentioned that we've been working on the analyticity and supershift. This is a paper that we just finished a few months ago and still only on archive. And that's where we try to address the gap between these two notions. And we do here the case, now we're working on irregular sampling. So we do the case in which the samples are equally spaced according to certain rules. So that 1 minus 2j over n would be one of the examples of regular sampling. But what happens if you allow irregular sampling? Can you gain something by allowing points to behave differently? A couple of articles more on physics, supergrowth, and sub-wavelength object imaging. That's probably the state of the art on the use of super oscillation for representation of for super resolution. The case of several variables that you saw a glimpse when I solved the case of the free particle, but in fact the general case is much more complicated and kind of interesting in many ways. And then what happens if we take different observables and we try to do super oscillation for different observables? That's just some of the recent literature that might be of interest. And then I want to close with an invitation. Every other year we do a conference in southern Italy, in Cetraro, on super oscillation. A conference only dedicated to super oscillations. It's a 3-day event in which everybody who's been working here, Barry, Aronov, Zeludiev, all the big names of these participate. If you have up to, I think, a couple of students that you might be interested in sending, if there is any interest that this conversation has had, we should be able to accommodate them and provide them a scholarship so that they could, you know, we would be paying for their local expenses, hotel, pickup, and stuff like this. So I offer this because if there is any interest in this, I think that's a very open field for both mathematicians and physicists. There's a lot of really beautiful math, and surprisingly also for people who don't really know much about physics, like me, but they are passionate about Fourier and other things. But also there is a lot of very interesting physics. And the conference we have really brings together the two groups. So we have about 20 talks in those 3 days, and those talks are equally distributed between math and physics. So feel free to reach out to me and let me know if there is anybody that might be interested. And so I stop here, and I thank you very much for your attention.